All right, welcome to the last one of the week. So, Thorsten Hertl, Freiburg, will be speaking about the moduli space using the Dominic methods.
Yeah, thank you, Marcus, for the introduction and also for the invitation to speak to you at such lovely conference. Before I start, I would like to invite you all to applaud the organizers for this wonderful effort and postage. Okay. Yeah. Today, in this afternoon session, I would like to continue with the morning sessions on the study of the two modularized spaces. And in this talk, we focus on a very special sub-question, namely to construct non-trivial elements in higher order groups of G2 modularized spaces. And I will show you how to do that in the next 30 minutes. In case of a specific example, and we will achieve this non-trivial element by constructing the kind of pop vibration of G2 manifolds. But let me shortly remind you what you may have seen this morning. The group G2 is a member of Berger's famous list of possible holonomy groups. Berger in 1953 couldn't exclude that group, and in fact, 30 years later, it was proved that this group belongs really to that list. Holonomy is, or the holonomy subgroup, is a global differential geometric quantity that measures what kind of additional geometric structure, what kind of constant geometric structure, additionally lives on my Riemann manifold. So the concept of holonomy is closely related to many types of geometry you may know and like Calabi-Yau geometry, Hyperkähler geometry, or in this main theme of this talk, G2 geometry, which is seven-dimensional geometry. This is a seven-dimensional realm. So let me remind you what this mystical free-form is. There are a lot of conventions flying around in the literature that are all slightly different, and in this talk I choose the following one. The model case for this G2 structure is the free form on R7, and I interpret R7 as a copy of R3, which I think of as the imaginary quaternions, and a copy of the quaternions website. And in my convention, the G2 structure arises out of the standard hyperkähler structure of H. So these forms alpha, they are just the imaginary part of the H-valued inner product. Got the Euclidean product, it's a symmetric product with values in R. You have the Hermitian product on Cn, takes values in C, and on Hn, you have an H-valued inner product, takes values in H. And this alpha is the imaginary part with respect to the complex structure I, J, and K. These are standard hyperkähler structures, and they give rise to a G2 structure. We also have seen this morning that the G2 structure actually recovers the Euclidean metric on R7 with this nice formula down here. So the group G2, which is defined as the stabilizer of this free-form, actually lives in SO7. It's a subgroup of SO7 because of a heavy inner map that fixes this free-form, but also fixes the metric and the orientation. We get a subgroup here. If you do not like that formula, or if you cannot remember it, that's not so bad, because we have an entire orbit of orbital free-forms. And it's an open subset in the set of all free-forms. So any element of this orbit actually does the job as well. So pick your favorite one. We use this open subset, this open orbit, to generalize G2 structures to manifolds. And these are just free-forms that have values in this orbital orbit, in this orbital free-forms. And again, such a section now gives rise to a Riemann metric and an orientation of that manifold. Same formula as before, because it was a pointless formula. So you may ask now, what kind of instructions are there for the G2 structure to live on a manifold? I mean, your manifold must be oriented, that's clear, because we can produce one. And the second obstruction is the vanishing of the second derivative class. So every spin manifold is also a G2 manifold. And this can be seen quite quickly using a spinorial interpretation of this concept, which I'm not going to introduce, but the topological obstruction against the G2 structure where the might only need two characteristic classes to vanish. So, although quite interesting, let us spice up our object of interest a little bit more. Let's add differential geometry to that picture. We can differentiate our G2 form with respect to the Levi beta of its connection of its underlying metric. And the resulting tensor is called the torsion tensor. So it is the differential geometric obstruction against parallelity, against being covariantly constant. So we call the G2 form torsion free if and only if its torsion tensor vanishes. That means if and only if the form is parallel. Just to rephrase what we have. The more important point is that the form is torsion free if and only if the G2 form is closed and co-closed. And co-closed means that the Hodge star of phi is 0, but the Hodge star operator depends on the metric, that in turn depends on the form itself. So the second equation is a non-linear elliptic partial differential equation, not a linear one. And this is the reason why this G2 geometry is so complicated. Linear PDEs are easier to solve. Okay, so if this torsion tensor vanishes, then the holonomy of the underlying method is contained in G2. But we are not interested in subgroups. We want to study methods where we group is the entire G2. And for closed manifolds, we can guarantee this with an additional topological ingredient, namely fundamental group. If you are the closed manifold, then the holonomy group is the entire G2 and not just a subgroup, if and only if the fundamental group is finite. In this case, the isometric group of the underlying metric is also finite, and the first Contriani cluster of vanish. So we have some nice instructions for the closed G2 manifolds, where the holonomy equals the entire group. There's another nice structure result due to Dominic Joyce, which says that the moduli space of all Thorsten G2 forms is a finite-dimensional manifold. And the manifolds, the dimension of this manifold equals the third Betti number of the underlying manifold question. Oh, that manifold here needs to be closed, I should say, because this is the result we like to Hodge theory. So, personally, I find this result quite amazing. It's not an abstract result. Dominic Joyce also wrote down local charts, and these are just given by sending an equivalence class of such a total G2 structure to a Serrano G class. This is a local formula of this. However, that result is entirely of local nature. The modular space itself may be, and information about the global topological properties of that space, these are rather scarce. So we know that this is not compact if it's not empty, because we can embed half ring just to scale your free-form topological constant. This is still the Thorsten free. And another result in that direction is due to Crowley, Sebastian Goette, and Johannes Nordstr. They gave examples of G2 manifolds where the moduli space is disconnected, making use of the analytical refinement of the muting variant we have seen this morning. However, so far, we have no knowledge about the higher homotopy groups. So, for example, the path conformance of this space, they may be contractible. But this is not the case because of our main result we were able to prove. We could show that Joyce's first example of a closed G2 manifold this has also a non-trivial, its moduli space has a non-trivial second homotopy group. In particular, this modular space is non-contractible. This also has to be known before because these generalized polar constructions, these Joyce examples, they are not really, you cannot really get your hands on with the new yet. So, yeah, maybe the rest of the talk I will essentially spend on the proof of its theory, but before I'm going to do that, I would rather take the time and present a short strategy of the proof. Naively, you would expect that we construct a map from the two sphere into the space of total 3G2 structures, then pass through a moduli space, and then compose the mass to some structure space, and hope that the resulting map is not contractible. It's not homomorphic constant map. However, this is extremely difficult, and I don't know how to do that, because it is extremely difficult to come up with G2 holonomorphic matrix, the G2 total G2 structures. We would have to construct the entire family, which is highly non-trivial, and then passing to a moduli space requires it to be even more non-trivial, because of the entire diffeomorphism. So instead, we use the diffeomorphism group, which we thought to get rid of by portioning it out to our advantage. Recall that the classifying space of diffeomorphism groups classify manifold bundles. So to make construct this example from the previous slide, we make use of the following data. We use the fiber bundle of G2 manifolds over SK, and the structure with this big part component of the diffeomorphism. This condition is always satisfied if the dimension of a base here is bigger or equals than 2. And we look for a fiber-wise torsion 3G2 structure on that fiber. That means we have a family of 3 forms that continuously depend on the base parameter, but maybe in a twisted way. Having such a datum, we can construct a map into a moduli space. How do we do that? We take a base point of our base here and send it to the fiber-wise torsion 3G2 structure. This lives on the fiber that is diffeomorphic to M. So we pick a diffeomorphism and put it back to our model space. Well, the choice of diffeomorphism does not really matter because we pass to the moduli space the relative portion of the diffeomorphic group. So we get a well-defined map from the base here into a moduli space. And of course, with the diffeomorphism we have, it needs to come from, maybe it needs to be a diffeomorphism that lies in different zero. So some compatibility is required, but we have this bundle chart. The first bullet point guarantees that we find such admissible diffeomorphism. Normally, you would expect that this construction doesn't really lead to something interesting, because we forget a lot of things. But in case of exceptional holonomy, this is true, because we could also prove the comparison theorem, which says that the canonical comparison map from the space of homotopy, from the homotopy quotient into the actual quotient is too co-connected, which means that this map induces an injective map on pi2 and an isomorphism on all higher homotopy groups. And the space on the left-hand side is precisely the classifying space for that data. So a map from SK into the left-hand side precisely gives me a datum of a fiber bundle of SK together with the torsion 3G2 structure, fiber-wise torsion 3G2 structure of that bundle. This is a pretty nice theory because if we can prove that the underlying vector bundle question is not trivial, then we know that this resulting map is not homotopy to a constant map. And proving that bundles are non-trivial, there's an entire field that is studied that question, namely differential topology. We have a huge toolbox available to prove such a non-triviality. So the upshot is here to construct this example from the previous slide. What we need to do is the following. we need to come up with an interesting fiber bundle that has a fiberwise Thorsten G2 structure on it. And this is what we want to do. Before I can explain you what a fiber bundle is, I first have to talk about the fiber, namely Joyce's first example. And what Joyce did was to construct the G2 holonomy trick on 7 manifold was that is usually referred to as generalized Kummer construction. So we started with flat 7 torus, the standard 2 structure on it that I showed you at the beginning. This is that invariance with the descent to a 7 torus. And then Joyce took a finite group that act on this torus by evolutions in a G2 preserving manner. That action is not free. In fact, the quotient is a flat manifold that is simply connected. And the singular set of this manifold decomposes into 12 disjoint copies of 3-dimensional tori. These tori have kind of a tubular neighborhood inside the orbifold that which looks locally like a cone with Z2, because Z2 things singularity. So locally it looks like this product here. Maybe I should have taken a small disk instead of the entire quaternions, but these are minor details. The next thing would be now to resolve these singularities. So, and we do this by blowing up these cone singularities, which means topologically that we cut off the tip of the cone, you get it here, and glue in the disk bundle of the cotangent bundle of CP1 along a common boundary. Well, the reason is that if I chop off this cone tip, I get a manifold with boundary. The boundary is RP3, rather T3 times RP3, 12 copies of it. And the disk bundle, the cotangent bundle of CP1, is a manifold with boundary. The boundary is again RP3. So we can glue these things together at a common boundary. The reason why we use this cotangent bundle of the CP1, well, first of all, it has the right boundary, that's good. But the nice thing about the cotangent bundle of the CP1 is that this is a hyperkähler manifold. Sometimes it's referred to as the Cauchy-Hansen space because it carries a complete hyperkähler manifold, complete hyperkähler metric that is locally, asymptotically locally Euclidean. That means away from the zero section, that metric converges very fast to the Euclidean metric. And for that reason, the Thorsten G2 form of this product here is also asymptotically locally Euclidean. This information allows us to glue these two G2 structures together on a common gluing strip. And if we do this in a clever way, then we get a resulting free-form pi, which is closed, which is also a G2 form, and which has small torsion. And then we can use Joyce's analytical sledgehammer, which says that if we have the closed G2 form with small torsion, then it can be slightly perturbed to a torsion-free G2 form. So, and therefore, the resulting manifold M7 has the torsion-free G2 form. So it's a Riemann metric as holonomy contained in G2. If we take a closer look at the underlying topology of that manifold, we see that this manifold is simply connected. This is just an iterative application of Untitled theory. And so the holonomy of the underlying metric is not just contained in G2, but it's the entire group. We can also look at the Betti numbers. I mean, V1 is 0 because it's simply connected. V2 is 12 because of the additional 12 twos here we use to resolve that manifold. And the third Betti number is a little bit more complicated, so trust me that this is 43. And the consequence is that the moduli space of this manifold is a non-empty 43-dimensional smooth manifold. So this was one before, and in our project, we needed to calculate its first quantity eigenclass, which we know by general theory must be non-zero. But we actually used Chern-Weil theory to compute first quantity eigenclass and observe that it lies in the integral lattice that is divisible by 3. So that means that if I have a smooth map from 4-dimensional manifold into my joint manifold, and if I pull the quantity eigenclass back in that map, integrate over this closed manifold, and I get an integer value that is divisible by 3. This is, I invite you to remember that context because this will be important data. Okay, so we have understood the fiber quite well. Let's go to the construction of the bundle. We need another ingredient, namely, we will construct this bundle by resolving the singularities that I've shown before in families. And that ingredient here, well, this is the non-trivial family. So we have this cotangent bundle of CP1, our Iguchi-Hansen space, and we turn it into a fiber bundle by pursuing the following Borel construction. This gives us a bundle with fiber T CP1 over S4 for modulo U2, which is N2. And another interpretation, I mean, you may wonder, why did we come up with that construction? The reason for that is based on differential geometry. We cannot use the symmetry effect. Observe that F04 is the isometric group of RP3, and this lives into an element in G3. But the Iguchi-Hansen metric, that metric has fewer symmetries. It has a smaller isometric group. And U2, well, which is U2, and U2 is the all. It only lives, it also lives stabilizer of this form by EH. So this is why we are using this construction. So this is the motivation to consider that bundle is based on differential geometry. We can reinterpret this bundle basically as a complex vector bundle over CP1 times S2. So CP1 is the zero section inside this cotangent bundle, and S2 is the base parameter. And we also get a complex vector bundle over it, which allows us to write down canonical embedding from CP1 times S2 into this Iguchi-Hansen bundle, but just taking the zero section. And the nice properties of this fiber bundle is that away from this zero section, this bundle is trivial in particular. It is trivial near infinity. This fiber bundle has a fiber-based torsion-free asymptotically T and G2 form on T3 times it. So basically a generalized construction I have shown you 2 slides before. And this fiber bundle is indeed non-trivial because the first country Argin class of its vertical tension bundle is -8 times the generator of this topology. If it were trivial, then the first country Argin class would be trivial, in fact. But it's not. So, right. We use this family basically to construct our bundle we are interested in. And to do that, we remember how this joint manifold was constructed. Yeah, I mean, we did it by resolving singularities of that orbital. So what we do now is we remember that construction. We chop off one of these disk bundles we do it in, take the resulting curve. So this is type view. Take the resulting manifold with boundary times CP1 times S1, and then glue in this twisted family instead. Yeah. So here on the left-hand side, we removed the trivial product of TCP1 times S2. We remove it, chop it off, and instead glue in the twisted family. I think you will do 2. And now comes the sketchy differential geometric part, that resulting bundle where we can do essentially the same gluing construction as before in the untitled Joyce case and obtain a fiber-wise closed G2 form with a small portion. At that point, we need to generalize Joyce's perturbation theory to families, but this is straightforward, and it's true. So we can perturb our fiber-wise total 3G2, our fiber-wise the closed G2 form to a total 3 form. Okay, so the upshot is that we have exactly constructed the datum we need to write down this map into a moduli space. We have this fiber bundle with a fiber-wise G2 form that with this total 3. So the only thing we need to prove is that this datum is in fact not trivial. But it's true, because we can show that the underlying topological fiber is already trivial. So our comparison theorem tells us that the induced map presented 10 minutes ago gives me a non-contractible map from S2 into the moduli space. Like this. So the only thing I owe you is the proof of that proposition here. And this is in fact quite cute, because it's essentially a number theoretic argument. So recall that we have this canonical inclusion of CP1 times S2 into this bundle of this family, and we can extend it to an embedding into this fiber. Now we take the first quantum class of the vertical tension bundle of this fiber bundle and integrate it along this 4-dimensional submanifold. For that, I mean, we only need to know the restriction of this vertical tension bundle to this 4-dimensional submanifold, which is precisely the vertical tension bundle of this equal G-Hansen space, because the 3-dimensional torus that doesn't contribute is equal G-Hansen space in both neighborhood of this submanifold. But we calculated that it was -8 times the generator, so the evaluation here is -8. On the other hand, if this manifold bundle were trivial, then the vertical tension bundle would be a pullback of the tension bundle of the fibers. And now we can use naturality of this pairing of homology and cohomology to transfer this to an integral of the first quantum class of the fiber along the singular submanifold, which we have already seen, must be divisible by 3. So we conclude that -8 is an integral multiple of -3, which we know to be false, right? So this gives us our desired contradiction, and the manifold bundle cannot be trivial. So let's recap. I've shown you a construction of a fiber bundle, kind of a hop vibration of G2 manifolds. And this hop vibration of G2 manifolds gives a map, provides a map from S2 into the moduli space of G2 polynomial matrix. And our comparison result here on the right-hand side shows that this map is in fact injective. So for a non-trivial bundle, this rise to non-trivial element there. And yeah, I hope I have convinced you, because this is everything I have to say, except that I would like to thank you for your attention.
Thanks very much, Thorsten. Questions?
So is there some analogous family of K3 services you can build to get construction with this?
I would guess so, yes.
Do you think it would give you like an advice to
Well, essentially I mean, I never really bothered to calculate that, but I'm pretty optimistic that it's pretty tricky. Because we change the complex structures. In the end, we never touch the totals. And we have this kind of construction of K3 services. So I'm pretty optimistic that this will smoothly probably.
I was wondering about this quotient map. show connect. So G2 to G2 mod D. Is that not a serial vibration?
It is. It is. It should be even a fiber. The fiber is.
Then I don't see why this stuff on the right will fit this necessarily.
I mean, well, I mean, these are basically two different sides of the same coin. I've never seen the proof of what you were saying, so essentially proved that in a kind of different manner, but this is essentially the same. Yeah. But if you have a reference for that, it would be.
No, I'm curious.
No, it's unlikely.
Okay. So
Can you start with manifold? Of course, the problem there is the finding constructions. I mean, essentially, so far, every G2 manifold I've encountered comes through some construction. And the moral principle would be if you have to make choices, and if you construct a family, depending on the choice to make, then you get a fiber bundle. If your fiber bundle, I mean, has a three-dimensional parameter space, like S3, for example, then yeah, you can apply this method. But these invariants are basically tailor-made to the constructions you are pursuing. So I haven't encountered yet a family where I have a three-dimensional sphere as a parameter space, but I mean, the answer is yes.
But I mean, the problem is you need a standard resolution which fibers over some sphere, and at least Joyce considers these product resolutions, and typically they have this.
Yes.
The huge empty space with light exception, and all the other spaces come in larger families, but applying correctly involved they have less symmetries. So we would be hard to fix that.
okay, if there are no further questions, thanks once again.